So this is a chance just to share. Thank you for remembering to record. So we'll have Rajesh give a presentation first, and we can have Q&A a little bit after that. And then also very important is to work on the milestones for the CI area. And like I said in Slack last night, I started a very rough draft just to have a skeleton and seeded with some milestones I can think off top of my head. Anand and I had a brief discussion yesterday, and so some of that is reflected in here. But it does need a lot of work for the out years. I didn't have a lot of good ideas what to fill in, but I think collectively we'll be able to do that. So any other items?
Well, just great to see everyone before Thanksgiving here. So grateful for the wonderful teamwork here. Of course, after this, we don't want to see each other again until after Thanksgiving. Happy Thanksgiving. Yeah.
Okay. With that, Rajesh, would you like to get started?
Sure. I might need to be able to share screen.
Yep.
Let's see if I can get it at the first try. Can everyone see the slides?
Yep.
All right, great. All right, well, hello everyone. This is a really quick overview of GeoEDF. I'll try to keep it short, but maybe spend some more time on some of the more, I guess, interesting slides. I know I might be preaching to the choir here on some of the initial vision and the goals of the project, but I'll try to skip through those really quickly and then focus more on the technical pieces. So the main vision of the project is sort of illustrated here. Some of our colleagues were able to come up with this diagram, which we thought was really nice. So on the left here is essentially the key challenge that we observed that made us sort of envision this GeoEDF project. So as I'm sure all of you are aware, researchers spend a lot of time, particularly in the geosciences, in wrangling data, fetching it from different sources, and then preparing it for use in their models. Some of the specific challenges there, particularly with respect to end-to-end workflows, is that you might often need to use several different resources. So for example, say a student is working on a project, they might prefer to use ArcGIS just to speed up the processing of the data. So they may download data to their local laptop or desktop, do some processing on ArcGIS, then maybe upload it to an HPC system, do some processing there, and then finally display the results or use it in a meeting or something like that. So there's really no sort of capture of the end-to-end workflow and the steps that are used. And if someone wanted to say reproduce that workflow, then it becomes pretty hard to do that. And this is particularly the case when you have students working on this, because you may have a student who leaves and then the knowledge is sort of lost with them. And this sort of this posted here sort of illustrates that this knowledge is really just encoded in some documentation that may be in some place. It's not really in one central location. So the goal of GeoEDF is what is illustrated here on the right. That's sort of the end goal, that a researcher can essentially come to a science gateway, define the workflow that they want to run. For now, it's essentially a YAML file that encodes to the workflow. In the future, you may have tools that help you maybe drag and drop pieces to create a workflow. But they can come to this gateway, define the workflow that they want to run, and then have GeoEDF essentially just execute it. And then everything happens in the gateway. The workflow stays in the gateway. It may run the workflow somewhere else on HPC, but then the data comes back to the gateway, and then the user can essentially publish that using the capabilities in the gateway. So they may get DOIs, they may get metadata extracted automatically. So that's essentially the end goal. And so really GeoEDF is trying to solve this data wrangling challenge, but at the same time, make these workflows more standardized and abstracted so that you can publish workflows, enhance reproducibility, and in the end, essentially contribute to fair science. So there's different components of GeoEDF, which I'll be talking about that's shown here in the middle, different pieces that we call data connectors and processors, and then how they come together to help you run workflows. So I'll start with an example, and this may all be things you've all seen in the past. So here is one particular example from our use cases from agricultural economics, which I think is one of the use cases in this project as well. So this shows a really nice diagram of the different data sets that are involved in creating this database for this particular AgEcon model, which is called Simple. And so you have data from, say, FAO, which is the UN Food and Agriculture data set, which has like crop data. And you may have other sociological data as well that comes together. You create a database out of all those data sets, and then you can use it for different models. But when you get down to the specifics of how all these things work, and this is actually a whiteboard where we were trying to work through just this first step of creating this simple database, you get into all the different messy details. So getting data from FAO stat, you realize that some of the data sets are zip files, and you have to go into a different JSON file for the catalog to figure out what data set you're interested in. Then maybe you can unzip that file and get to a CSV, but then the Simple tool doesn't really work with CSVs. It has this really custom format called HAR files, or I think header array format. And previously there were only Windows tools that could produce those files. And so even just one step becomes really complicated when you get into how do you get to the final product that you're interested in. And of course, there's other things you need to keep in mind. For example, data may only be available for a certain time range, and then you may have to go to other places for other data sets. So how do you simplify all of this, and how does GeoEDF help in this scenario? So we really organized GeoEDF around these 3 design principles, and this is all motivated by these different use cases. So the first principle is that we want to take a research workflow that a researcher comes in with, and then break it first into 2 kinds of tasks, basically data acquisition tasks that are trying to reach out to a different database or a remote repository, some other data source, and then fetch that data. So those are the data acquisition tasks. And then data processing tasks, which may be transforming data from one format to the other, maybe converting, splitting data, reprojecting, all kinds of geospatial operations. And of course, this is not very generic. I mean, it's intended to be as generic as possible, but obviously we realize that not every workflow can be split into these pieces, but a majority of them can. So once you've split it into these 2 kinds of tasks, then the next goal or the next principle is to make reusable building blocks that you can use to accomplish these tasks. So that's not really specific to this one workflow. Maybe it's a little more generic than the specific workflow. And so once you have these reusable building blocks, then you can essentially have people be able to compose them into the workflows that they need. And then finally, along with these building blocks, we want to integrate whatever cyber infrastructure features you want, metadata extraction and other pieces, so that you can essentially use these building blocks to promote fair science at the end. So in terms of technology, that essentially maps onto what we call data connectors and data processors. So the data acquisition blocks essentially become data connectors. They may reach out to different repositories. They may implement various protocols. So if it's just an HTTP or FTP site, then that's pretty straightforward. If it's a threads that is exposing data through an OpenDAP server, then you may need to use OpenDAP protocols to access the data. So those are the data connectors. Data processors can implement different processing operations. So it can either be domain agnostic, just typical geospatial operations, or domain specific operations for that particular domain. And then the GeoEDF workflow composer essentially allows you to compose these connectors and processes together into end-to-end workflows that you can then run. So here are some examples of connectors and processes. This is just to give you an idea of the different remote repositories that are available and the kinds of data sets that you can essentially access from them. We haven't built all of these data connectors, but as use cases come in, then we try to look at what remote repository can provide that data, and then how we can write a connector to essentially access the data from that remote repository. So NASA, there's obviously several different DACs that provide data from the different NASA sensors and satellites. USGS has several data sets that are useful in hydrology, and of course, all these other sources as well. And at the bottom here, there are some that we haven't really been able to find an API yet. So if someone is interested in data from those sources, then there's things we need to look into on how to accomplish that. Data processors, I touched on this briefly. So domain independent ones can be these standard geospatial operations here. In hydrology, you have their specific processing operations that are maybe somewhat common to most workflows. In digital agriculture, there's a couple of others. And then in the ag econ, there's usually some downsampling that happens, especially when you're going from global to local and then back to global. There's different kinds of resolution changes that happen there. So downsampling and aggregation, and then different models that you can run as a whole, as an individual processor. So once you have these connectors and processors, then the GeoEDF workflow piece is really two separate things. So one is the workflow framework, which we use to essentially standardize these connectors and processors so that a person who's writing a workflow or a connector or processor can follow these standards, and then that makes it usable for anyone. So it's not like each connector and processor is its own thing. It exposes a standard interface that you can use to string these things together so that you don't have to know the specifics of what the connector or processor is doing. You can be assured that you can string them together as long as you have the right data types. So the framework essentially defines the syntax and semantics of how you define connectors and processors and how you can compose them into workflows. The engine then takes these workflows that you build out of composing connectors and processors and then actually runs the code in the connector or processor. So if you again look into the software side of things or the technical side of things, connectors and processors are actually implemented as Python classes. We use the YAML syntax for defining workflows, so you can string together connectors and processors into a workflow in YAML format, and then those YAML workflows can then be transformed into a sequence of execution of connectors and processors. And really what you're doing is instantiating those Python classes and then executing methods on those Python classes. So I have an example here that may somewhat help to make this more specific from the abstract concept. So here's a really simple toy hydrology workflow example. You have a watershed that you're interested in modeling. Maybe there's one variable that you're interested in, for example, the leaf area index, and you know that can be obtained from one of these NASA DACs from one of the MODIS data sets. And what you're essentially trying to do is take this watershed map, but then there's obviously it's a shapefile, different polygons. You want to calculate the weighted leaf area index for each of those polygons in the shapefile. And then once you have that, then you do further steps in your hydrology workflow. So if we were applying the GeoEDF principles, the way you would transform this into a GeoEDF workflow is that obviously the acquisition from NASA, that would be a connector. This processing that you're doing here, essentially what it's doing is it's taking this HDF file and the shapefile and then doing a mask and aggregate operation. And so that would be a processor that takes an HDF file and a shapefile and then does this operation. So the GeoEDF workflow would look something like this. So you have a NASA DAC, you have a connector that's taking in data from NASA. Then you get an HDF file that's combined with the local shapefile that the user provides, and then it gives you a shapefile at the end, which is this weighted average per polygon. The reason we need a specific connector for NASA DACs rather than just using HTTP GET or POST is because NASA has you log into the Earth data login portal before you can access data from NASA DAC. So you need to do some sort of work there to first log into Earth data and then redirect and get the data. This is the same workflow represented in our YAML syntax. So as you can see, it's essentially field value pairs kind of with different steps here. So you have the numeric index of the step. So the first step is this NASA input step for the data connector. The second step is this data processor. And as I mentioned before, connectors and processors are really just Python classes. So here, NASA input is a Python class. These are the arguments to that Python class, or essentially the class variables. And you have field value mappings here. So the NASA input in this case takes three parameters. One is the URL, so the DAC endpoint that you want to get the data from, and of course your username and password for the Earth data login. And the password is left blank, and then the user is prompted when you actually run this workflow. There's one thing that we added on top of data connectors, so to essentially make it more generic and more usable. So we have this notion of what's called a filter, and filters can essentially provide bindings for variables that you use in a connector. So for example, here, say you wanted to get data from a NASA DAC, but then you only wanted to get data for this particular watershed. So typically what any researcher might do is they might just download the bulk of the data from the DAC and then just filter it to get the data that they needed. But then here, what we try to do is pre-filter it so that you're only fetching the data that's needed. And particularly in the case of these NASA DACs, often the data is organized based on the date range or the spatial bounds. So for example, here, this here encodes the MODIS grid number. So that's the horizontal and vertical grid numbers. So you can often use filters to sort of pre-filter the data that you're interested in. So in this particular case, we are using this datetime string filter so that you only need to fetch the data for the dates that you're interested in. And the advantage with this is if, say, you wanted to rerun this workflow for a different date range, then all you had to do was just change the dates in this filter part here at the bottom, and then you can essentially rerun the same workflow, and it would automatically set these variables and then get you the data that's needed for that particular date range. So you wouldn't have to really go in and change things in the URL manually. And then just like any other workflow, you can reference other previous stages here. So for example, here you see this is a connector that's downloading the data from NASA. Then this workflow, the data processor here is referencing the HDF file from this first stage here by having this $1 here for the HDF file argument. This is a local ship file. And then since these are all Python classes, you can essentially provide Python objects like lists as arguments to them. And so this is a two-step workflow where the connector runs first and then the processor runs second. So the way the workflow actually runs in HPC is through the use of Pegasus, which is this workflow management system that some of you may be familiar with. And the reason we use Pegasus is because it has support for dynamic workflows, and also it makes it very easy to run workflows on HPC. And the reason you need dynamic workflows is because, as you can see here, these filters may produce more than one value. So for example, if you had an end date as well, then you would have multiple dates here from the date string. And then you might have multiple HDF files that are produced. And you may want to run this, the data processor in parallel, essentially, to make it more optimized. But then since you don't know how many files are generated beforehand, so then Pegasus will actually dynamically construct these workflows one step at a time. So you have the first phase that's run, then you know how many data sets have been downloaded. And then the second step here essentially runs in parallel by instantiating a variable for step one for each of the HDF files that have been produced in the first step. And that's essentially what this is illustrating, but I'll skip over this. The only point I wanted to mention here or call out here is that these connectors and processors, as you may have realized, have a lot of arbitrary software dependencies because some of them may need GDAL, others might need, say, pandas or other Python libraries. And so we use containers so that they can run seamlessly across different HPC environments. So all of these connectors and processors are essentially built into Singularity containers that can be run on HPC. And the way we build these Singularity containers is through just GitHub pull requests. So all our connectors and processors are managed in GitHub. You can contribute them through pull requests. And then we have a GitHub action that's set to automatically build these Singularity containers for each connector and processor. And then the workflow engine essentially queries this container registry and pulls the container that's needed for that particular connector or processor. This shows sort of the integration into any CI environment. So here at the bottom is the GeoEDF workflow engine piece. So if your CI environment has Python support in it, then we can install the GeoEDF workflow engine there. We need the Pegasus middleware for essentially submitting workflow jobs to HPC and getting results back. So that needs to be deployed somewhere. And then the workflow engine essentially talks to Pegasus and works with Pegasus. On the top here is the contribution pipeline. So if you have connector and processor classes, you contribute them to GitHub. Then the GeoEDF framework is combined along with that and built into a Singularity registry or a Singularity container. And our registry is currently hosted on AWS. And then the Pegasus middleware essentially pulls the image as needed when it needs to run workflow. I'm conscious of time, so I'm gonna try to go a little quick, and then I can obviously answer questions. I think this is pretty much the end of the presentation. So there's different options here. We have 3 different deployment options currently. So our primary deployment is on the My GeoHub gateway. So My GeoHub, as many of you may know, is public gateway based on Hub0. It has support for containerized tools, and it also has Jupyter deployed in it. So GeoEDF, the workflow engine, is actually deployed in the Jupyter notebook environment. As you can see here, this shows how you can essentially use Jupyter to instantiate a workflow from a YAML file and then execute it and then get the results at the end. And all jobs are submitted to the hosted cluster at Purdue right now. We also have a standalone Docker image in our GitHub repo that we built for the EarthCube conference. This actually has GeoEDF, Pegasus, and a local Condor pool all in one single container image. And so you can just download this container to your desktop or laptop and then run it. And then you can actually create workflows and test them all from just that one container. So it'll just run in the local Condor pool in that container. And right now we're actually working on this other standalone, more scalable version based on Kubernetes. So we'll have the Jupyter environment for the workflow engine, but then a more scalable Condor pool alongside it so that you can run more jobs or much larger workflows on that. I think that's the end of my slides. We did have a couple of slides on our streaming support in GeoEDF, but I think we'll talk about that in a future meeting. I just wanted to flip to that and then put these links here. So that's our main GitHub repository. It has all our connectors and processors and the code for the workflow engine. We have a read the docs for documentation on the connectors and processors. And then that's the Docker container that you can download and use to run locally, essentially. So I think that brings me to the end of the presentation. I know I ran through really quickly, but yeah, I can answer any questions. I think there's something in the chat. Josh asked. So Josh, to answer your question, it's primarily YAML, but then the syntax is very GeoEDF specific. So you have to have certain keywords, like input essentially refers to an input connector. And then these are essentially Python classes. And so when the workflow is being validated, it's going to look to see if these are existing connectors or processors in the Singularity registry. And so it's kind of YAML, but then it has additional validation on top of it. It requires certain keys in there.
Yeah, that's always been a particular conundrum. Let's say that there are many of these workflow scripting languages, vocabularies. They're very similar to one another, but not identical. So coming up with a language that really lets you convert from one to the other has been quite difficult. I've had a number of testbed participants who've been working with CWL, and it's not been bad, but we're sort of evenly divided between those that think it's too complex and those that think it's not complex enough.
I guess I'm in the first camp there. We looked at CWL. We thought it was too complex for our needs, and we figured it's going to be a lot harder for our researchers to write the workflow in CWL. And I think once we move to a more drag and drop kind of model where the end user is not really exposed to the syntax, then we might be able to use a more standard language behind the scenes. But for now, we figured if you're going to be using Python classes and key value or argument value pairs, then maybe this is the best we can do for now.
Yeah, another thing to keep in mind is, that behind the scenes, if you're using something like CWL as a mediator, then people can work in whatever language they're accustomed to, but you can provide some translation service through that means. So, as long as somebody figures out how to map it into the common language.
Right. Yeah, I agree. Yeah, it's always good to stick to standards and things that more people are familiar with, but yeah, sometimes you just can't do it.
Yeah,
So
I'll chime in that. So I think, understandably, for our domain scientists, it would be hard pressed to ask them to turn these into more abstract connectors and processors. So as a first step, we're working with them to help them do that with the goal of, these things can be reused by others, can be more reproducible. So for the true end users who happens to need similar data sets, these will be either provided as, a template that they only need to go in and change dates, or have some sort of a user interface that they can just fill in some fields and get the data they need. So there are several ways we're planning on connecting, filling this gap. So I guess we have two, right now going forward, we have two directions. One is to really put this in the hands of the domain scientists. And then the second one is really for the CI professionals, right? To make it easier to install, and also to be able to integrate into any Python-based environment. So I think, Rajesh, your third option is what we call light, right? GeoEDF light. So it'll be much easier to install and not tied to Hub0 and other frameworks.
May I ask a question?
Oh,
sure, go ahead.
Is it to address to Jeff or me?
Oh, either of you, I guess.
Okay, since I'm already starting to talk, maybe I'll continue. Thanks for a nice overview of GeoEDF, Rajesh. Two questions I have. One is, Carol just alluded to it. Who are the end users of GeoEDF at the moment? Are they, scientists, students, faculty, people in agencies? I'm just, interested in knowing that. And the other question I have is, can users bring their own data sets and integrate it with the other data sets that you provide access to?
Yeah, so to answer your first question, so this was really, I didn't have that slide here, but this was driven by 4 main use cases. So one of them is from hydrology. Venkatesh was in this project as well. So this workflow is actually from one of his use cases. So they had built a tool called HydroGlobe that allows you to do essentially this masking and aggregation for different NASA data sets. So they have one for MODIS, one for SMAP, which is the snow moisture, I think, or snow something, soil moisture, or snow something. So that tool essentially is doing very similar things, but then it's always taking a shapefile and an HDF file and then masking and aggregating it. So one goal we had here is to simplify that tool a whole lot, because if you look at the code base for that, it's very complicated. But then with GeoEDF, you can essentially just write one workflow for each of the 4 different choices there and then use it there. But obviously that's just to show the performance improvement with GeoEDF. But right now we are working with Venkatesh and his students who are trying to do this processing across watersheds across the whole US. So they are doing this machine learning workflow where they take the gauge features and the stream flow data, and then they want to essentially do a prediction of stream flow using both the physical features of the gauge and other details. But then if you look at their workflow, the student right now, just because of the lack of resources, they don't really run this on HPC. The student usually runs this on his own laptop. So then he is forced to only model a very small part of the US, a very small watershed, because one, getting the data is pretty complicated, and then he has issues getting the data. And then the other piece is obviously getting all this data, converting it into a format that can be used in training his machine learning model. So one use case is one for Venkatesh's tools, but then maybe more on making his students' workflows more efficient so that they are not really spending a lot of time doing this on their local laptop. So just transforming it to the cluster, but then using GeoEDF to sort of streamline that workflow. That's one use case. The other one is the one from AgEcon, which is Tom Hurtle's colleague, Uris, who created this particular workflow. And so he wants to use this workflow essentially for creating these different databases that are one for just non-gridded versions, and the other one is the simple G is for this gridded version that can make the local to local more efficient to work on. So I guess in answer to your first question, those are the 2 main users. One is Venkatesh and his students. The other one is Tom Hurtle's colleague who's building this workflow. And your second question was on people bringing their own data sets. So the connectors really are designed to get data from remote repositories, but then not have the researcher bring it to their local laptop or desktop, but then directly bring it to the HPC where the workflow is running. So we haven't really had a use case where someone had to bring in their own like large local data sets. I guess it depends on where that data is hosted, but the connector is not really going to be, I guess, taking the data from their local gateway account or something and then uploading it. But if it's stored somewhere else on an SFTP site or something, or they are currently providing access through Globus, then we may use the connector to be able to use that data set in a workflow, but then it's not really, I guess, trying to solve that challenge yet of making their local data more usable.
But technically, I guess if I look at it from a higher level, these are just going to be connectors, whether it's local, right? So the framework technically could address that. And also with the lightweight deployment, you could think of installations that you really bring the data processors to where the data is. So in long run, I think that picture would be a fit.
Yeah, on your last point, it's a marvelous concept to move your processing, and computation to the data or near the data. But when I look at this list, that's in front of us, none of these will provide you the resources to bring your workflow and software analysis visualization to their systems. So unfortunately, that concept, as wonderful as it is, still has a lot of challenges.
Right.
Well, that's not how it's implemented, though. The way it's being implemented is that all of these organizations are then uploading these data sets to one or more cloud platforms and inviting people to use the data in those environments. So, certainly NASA and USGS are doing this and planning to do even more of this. The challenge that a number of OGC initiatives have addressed is, well, this data set is on Google compute platform, this one is in S3, how can we more easily get applications to work, cross-platform? And, the other, the optimization problem is, okay, where would locating the application create the least time and expense of the IO processing? But there's certainly these organizations have realized the dilemma that you've posed, Mohan, and are addressing it by staging their data sets in these more compute-friendly locations.
Yeah, that's a very good point. And I'll just put a plug in for NOAA datasets, which is not on this list. NOAA has a lot of data. The reason I mention is because that's our bread and butter in terms of providing access to NOAA, datasets and streams.
Absolutely. I think that's actually quite related to what we'll be discussing in this group, right? So there are all these different platforms, different data sources, and people need different things. So how do we collate those and assemble these services and capabilities to deliver what they need, right? So that, I think that's the central kind of challenge to all of us, to provide data on demand. We're not there yet, but with all these brains, maybe we can figure a way out.
I had a couple questions. Do we still have some time for questions?
Sure, let's do that.
Rajesh, early on, I think you mentioned that the workflows get stored and that actually you're issuing DOIs for workflows. Did I catch that right?
Not yet, but since you're, so for example, if you were on my GeoHub, your YAML workflow is essentially in your Jupyter environment there. So we don't do DOIs directly, but then in my GeoHub, any data that's in your tool environment can essentially go back to what's called the projects environment, from where you can publish them. And then Hub0 essentially gives you DOI. So it's not very seamless, but then just the mere fact that it's on the gateway essentially means that at some point you can go through the publication process and get a DOI for it.
Yeah, so my question around that was, how would you handle workflows that have lots of external pointers to resources that you really have no control over? So you publish the workflow, you publish it, you give it a DOI, and then all of the connectors eventually break because somebody changes their service or their interface or the location of their data or any of those sorts of things.
Yeah, that's a big challenge. I guess that's something we've struggled with quite a bit. I know in the past we've thought that maybe we should package that as well, but then I mean, obviously you can't package large quantities of data and publish them alongside your workflow. So I guess there's really maybe no obvious solution to that yet. So things like local files, that our plan is that, so for example, in this workflow here, since you're using a local shapefile, obviously you can publish those alongside, so you can package that with your workflow and then publish that along with the workflow. But then the remote data sources, unfortunately, there's really no, I guess, yeah, I don't have any obvious solution to that on how you can control that, or how you would essentially prevent your workflow from not being reproducible at that point if no one can, if the remote data source disappears.
So this is probably quite general, right? So unless you version the data, and for these large repository, I don't know how they version the data. Some changes are maybe considered minor, others are major releases. So perhaps this is one of the things that the Institute can have some impact or guidance. I think that would be very useful for the different services.
Yeah, I mean, I could see a lot of utility in a system like this, even for smaller workflows
Mm-hmm,
that maybe don't involve ginormous data sets, where
mm-hmm,
there might be some practical limits at which you say, well, we can no longer package the data with the workflow, but there may be
mm-hmm,
a boundary below which you say, we can package the whole thing up. And since the
mm-hmm.
whole thing is containerized, the whole thing is reproducible. And I don't know where to draw those boundaries. Obviously, that's a hard question, but
Yeah, I think that it's great, you know, while you're leading this area. So I would defer to you. And also I think that would be a great thing to do. You know, honestly, for this project, there are so many things we can do, and we only have very limited resources. So we opt to focus on, you know, getting the framework set up and having portable deployment versus, you know, really think through these very complex reproducibility issues. So we would love to have guidance, and especially, you know, in terms of how to document, associate information with these workflows. I think on that front, we definitely could use a lot of help.
yeah. My other question was about iterators. I'm assuming that the workflow system that you're using supports looping and iteration and repetition. And do you support branching and parallelization and that
No,
sort of stuff?
there's no complex control structures here. The only iteration is the like whatever parallelization you can get out of the bindings, essentially out of the different steps. So say if you had 50 different HDF files here, then this would essentially only instantiate one of them at a time, and then you would have 50 separate jobs there. And recently we had one where we were fetching streamflow stations, and we had like 2,000 stations, and so we had like 2,000 jobs in the Slurm queue on the HPC system. So that's pretty much the amount of control structures we have. We don't really do, I mean, we haven't really seen a need for iteration and branching. We are now seeing that with model coupling, especially because if you wanted to run this workflow until steady state, then you might need to essentially iterate this workflow until some condition is met. And I guess obviously you can expand the syntax to sort of support that. And the engine can do that as well, because behind the scenes, Pegasus, I think, is able to do some of those things. But we haven't had a need for it. But I guess that is on our radar to have like branching, conditional branching, and iterations.
Yeah, okay. I mean, that's sort of what I was thinking of when you were talking about this. I was like, well, how far down into that into those weeds could we go? Is there actual support for modeling here, or is this more focused just on making the sort of larger scale tasks run in sequence? And it sounds like the second.
The second, yeah,
thing.
yeah, it's more on
Sequencing things. Yeah,
sequencing.
sorry.
Yeah. Yep.
Yeah, thanks.
This is good discussion. There's one area, I guess, that would be needed is to how this could be integrated into the iGuide platform. But I think probably a better time would be after a couple more presentations of other CIs. We can have a more productive discussion then. Also, I'm conscious of time, and I do want to get to the milestone discussions. So I'll just say thanks, Rajesh, and thanks for everybody who ask questions and provide the guidance on various things. So I'm really glad to see all these experts in this group that we can now get help when we have questions. So thanks a lot. Let's move on to the milestone documents that we need to fill up. Let's see. I'll share my screen. Can everybody see it? Okay.
Yes.
So I don't know if anybody made any additions yet. Okay, so the list is what I have based on my discussion with Anna yesterday. So you can see here, I copied some of the all of the tasks in the CI core services and capabilities. And I also looked at the proposal and extract out, the key elements we said we were going to do. So here's the full list. And then on top of it, we feel that there are some cross-cutting tasks. For example, the science gateway that we proposed as an entry point for users to find and find things and share data model and stuff. That would be cross-cutting, and user personas that would be used to guide all of the tasks probably. So those two are first that come to mind. And so here I just put some stuff thinking, okay, by second quarter, we should be able to do some of these things. So I just laid them out. I don't know whether the time frame makes sense or not quite. And then I put in, we're gonna do quarterly minor updates, major release every 6 months. I don't know how reasonable that is. We can always put out releases. So it may also tie to our sprints if we do sprints. So I think there are a lot more details, but Xiaowen, so my understanding is that we're trying to come up with milestones for the execution plan. Is that correct?
Right. And it could be more specific, I think, for the first year, and beyond the first year, we could be pretty coarse in terms of the details.
Right. So I cannot think beyond year one. So if you look at the attempt here, so I felt like, okay, let's look at the data on demand. So by the second quarter, year one, which means March, right? We'll make, for example, we'll make existing data connectors and processors accessible to iGuide researchers, and we'll be able to identify the initial data sets needed to by the science team. And so some specifics here, and then developing new connectors and processors by the third quarter. I don't know, it really depends. Part of this is depending on whether we can have clear requirements, so that the underlying assumption is that we have this very timely interactions with the science team, and they are able to articulate, how they're gonna do these convergence computations, and we abstract out the requirements from there. Given that I've worked with Tom's group, Venkatesh's group, a couple other groups, it always takes a lot of time for the science team to figure out what makes sense to do in their domain. So that's why I think some of these I struggled with the timeline. And for these other areas, so I put the names in here. So these names were what we put down in the proposal. And so I would ask those folks to really take a close look at these sections that has your name on. See if these are reasonable. I'm sure you would want to modify, add, or move things around. And if we can flesh out, like Shawan said, the first year, and then maybe looking beyond the horizon and put some major things in the out years that would help with the execution plan. It gets really in some of these. So what are your reactions?
Shawan,
I
can you
also put the
can you
pictures here, so these may be helpful to kind of regurgitate our memory.
can you clarify the execution plan? So is this something formal we have to send to NSF?
Yeah, this is what is expected of us as part of our Institute Governance Management Plan. My understanding is we will not have to be married to some really nitty-gritty level of details.
We also need to be careful what we put in, right? So
Right,
at review
absolutely.
time, the panel would have this, and they would say, okay, you say you are going to do this.
Right.
Did it happen or something like that?
And
Yeah,
is this
so
something that would be revisited annually?
it would be, I think, refined annually, and it would be sort of serving as a benchmark document for NSF, just to easily see whether we're on the right track. And again, as Carol indicated, we don't want to have very nitty-gritty details here, because with that details, it's kind of hard to match, right, given the nature of our project, to that kind of level. So we want to be reasonably generic and using as much as lay audience language so that NSF and potential reviewers would be able to say, oh, you know, these folks know what they're doing and they're on the right track. So that's the kind of goal.
Yeah. So on a quick glance, Shawan, what do you think the language I was using? Like, are these specific enough but not too detailed, or is it too detailed?
I think this is at the right level. We might even want to further abstract so that, again, you know, for instance, something in my head, we could say more of a binary thing, you know, for people to check off, you know, possible milestones. Say we would establish a data repository for the project. You know, that's a binary thing. You know, if the check that off, we say, oh, you know, we declare victory and move on. So when my understanding, when you come up with this list of things, there's a sort of a binary as well as a degree of success we need to consider in our mind, you know, whether, you know, it's binary is to say, oh, you know, yes or no, or degree of success would be, you know, excellent, very good, you know, outstanding, that type of thing. Even ourselves could say, oh, we are on the excellent scale, right, of doing these kinds of things. So keep those, but I think the structure here is looking good. I think using the tasks we put in the proposal, and just keep in mind when we put down these bullets, we ourselves know, you know, whether this is a binary or is a degree of success thing, as a quick check.
I think that's a good example, the data repository. For example, I was thinking, okay, we can say establish the initial data repository, and then in the out years, basically you're just going to expand because we don't have any specifics, right? So we'll just have new releases of the data repository each every 6 months or something like that.
You know, the second follow-up to that would be interoperate our data repository with community data repositories. And then, you know, when that happens, we would say adding services on the data repository, you know, from the representative community projects in the institute. So it could be incremental. Again, preferably binary if if you could say yes or no, but if needs to be degree of success, give ourselves some advantage, meaning we could in general be positioned to get an excellent rating. But I'll certainly take a pass. I think the structure is good after this conversation. You know, folks, because you put folks' names under each of some of the tasks. So for folks, you know, have your names there, you should go take a step, right? Register your thoughts, and then, you know, Caroline and myself could massage these things again to avoid nuts and bolts details, and come up with something generically applicable to NSF and us.
Yeah, for example, I was thinking to make it more general, higher level, for example, saying instead of data connectors and data processors, more say the current, making the existing CI services and capabilities for data acquisition and processing available, something like that, right?
Yeah, that's a very nice.
Yeah, so that would be much more easier for people to know what we try to do.
Right, and certainly avoid you know, jargons as you just did.
Right. Yeah. Yeah.
Yeah.
Okay.
So Shawan, question like when Carol and I discussed, we came up with this kind of a structure to doing it for like quarterly for year one and maybe half yearly or something for year two, if possible, or maybe even yearly from year two onwards. Should we go all the way till year 5, right? That's kind of our goal.
Yeah, we need to go to year 5. I think this is a whole project document. So, but as we go later, even what we put together for the management coordination plan at the proposal stage, we could even count on some of the sort of tabular things we included in that document. And I just got the impression NSF actually is pretty happy about our management coordination plan. I mean, with that kind of 3-page budget we had, now you go to year 4 or 5, everybody understands this is a prediction task. No one's going to be perfect at from this point. But after learning from Rajesh's nice presentation, I even got quite a positive feeling, right? You know, this is such a powerful team. We already got some quite valuable work on the ground. You know, the question is here to help each other and help pull these capabilities together and to address the gaps, and at the same time enhance what we're already doing individually.
So I would ask everybody to go in and really edit and add things, and change the language and all that. And I don't know if people can spend some time today. We're hopefully next Tuesday. We have a meeting next Tuesday, right?
Yes.
Yeah, so hopefully we have a more or less ready document to send to Shawan after next Tuesday. So we can look at all of it next Tuesday, and then just make final adjustments.
Yeah, I think this kind of is the structure. I'll use that for other teams as well, because I think after our discussion yesterday, I thought about it. This was kind of the structure we'll follow, and maybe each of the teams can come up with their own documents, and then we combine them all together. But Carol, I guess I see many of the people have left, so maybe we'll follow up with them on Slack or via emails to people saying, especially the people who are listed as the first in that list are maybe the owners of that section,
right?
Just so that we know what is needed. Everyone knows what is expected from them.
Right. Yeah. I'll get that email out.
Yeah. Thank you.
Okay. Thanks, everybody. I guess we're losing people, so.
Hey, and just really final thought too. I've only been on a couple of these, these agreements versus the normal, grant. I think it's okay to undersell a tiny bit, and then have overperformance in your first report. Like, I know but I've never write this in email, but oh, we expected this, but oh my God, we got this. I think they like this sort of wow, you're great and only getting better.
Yeah, that's always a good strategy,
that,
especially at this point. We don't really know, we don't know what to expect yet. We have stuff, and then the science team wants to do stuff. So that's as much as we know.
Yeah, I think that's a very nice strategy. It's underselling is really good now, because we are not actually expecting them to give money or anything for this, looking at this document. So underselling and then overperforming is better.
Smart idea, Steve.
Yeah.
Completely.
Been there, done that. So. All right. Well, thanks, guys. This was really educational. So
thank you.
Happy Thanksgiving.
Thank you.
Thank you.
Yeah.
Have a great Thanksgiving, everybody.
Yeah.
Thanks a lot.
Bye.
Bye.